Hello and good afternoon. Thank you so much for joining this talk. Really happy to be talking about Node.js and JavaScript. I'm first time in France and Paris, really cool place and really excited. So I'm Gireesh. I work for IBM India Software Labs, basically for a team that develops language runtimes for Java, Node.js, and Swift. I'm a Node.js collaborator and a community member. I'm also a member of the technical steering committee for the Node.js. One of the key responsibility of a technical steering committee member or a collaborator is, apart from developing and maintaining the project, is to assist newcomers who come onto the project and help in ways I can. So Node.js is one of the top project in the whole of the GitHub. It's highly vibrant, highly active, highly open, and highly inclusive. So if you have skills in JavaScript and a bit of C++, and if you're interested in participating in the Node.js core projects, welcome, and myself and my team are happy to help. Um, Coming to the today's topic, basically tracing and uh, logging in Node.js and V8. For any programming language, the first thing to do for debugging your application to see what went wrong, etc., is to put a printf statement or a console.log statement. Uh, that's the most trivial, most natural, and most generic aspect. But then, if you want to look at the application from different perspectives and you want to do it in an iterative manner in the phase of your development, this is not really scalable, and it's like a trial and error. So once you develop your application and you want to look at the different facets of the application from different perspectives, the virtual machine, the garbage collection, the just-in-time compiler, and the functions, the parameters, the variables, the return values, and things like that, you better make use of the most versatile and comprehensive set of tracing tools, tracing options that are available inbuilt into the language runtime, rather than monkey patching or applying source level modifications and figuring out what is happening. So that's the whole essence of today's talk. Though these tracing aspects are specific to Node.js and V8 JavaScript engine, the concepts and the principles can be applied to any language runtime. Now, before we actually talk about tracing, one of the key aspects which I think most of the newcomers to Node.js really wants is the basic principles and the premises of asynchronous event-driven architecture. The people coming from other programming language ask the key questions such as what is a callback and how does the IO driven workload happens underneath. How do you retain the context when you switch from one callback to the rest of the code and things like that. So predominantly uh, people who come to Node.js have a set of difficulties in getting onto the basics. Even if you're a JavaScript developer who has been working in the front end, when it comes to the back end, there are some subtleties which need to be sorted out. So we spend some 5 to 10 minutes on that aspect, then we look at the tracing tools. Okay, so look at this chart. This shows the amount of time that is taken for a unit amount of data to be transported from one endpoint to another in a computer system. An endpoint here would essentially mean any location in the computer system that can store a piece of data. And the piece of data can be as simple as a byte. As you can clearly see, the first set of endpoints, which are the registers, the cache, and the main memory, the latency that's used for transportation is in the order of nanoseconds, 0 to 100 nanoseconds, whereas the bottom 3 items, which are the secondary memory and the network, it's in the order of millions of nanoseconds, which is milliseconds. I kept a demarcation line in the red line. Basically, that means the secondary devices are external manufactured devices, and it has physical drivers to transport the data, and it involves a lot of operations. In computer science, the items which are above the red line, any computation that involves operation in the endpoints in the above red line are called CPU bound operations, and anything beneath are called IO bound operations. So as you can clearly see, the IO bound operations take a lot of time. And take the classical example of a web workload where you have thousands of concurrent connections, and one of the thread which is involved in a transaction. Any transaction in a web workload requires an IO, at least two IOs. One is to intercept the request, and one is to pass back the response. And depends on your microservices or the other backend services which you want to connect. All these things involve IO. So the more the IO, the thread gets blocked on the IO, and the time taken for the block is in the order of milliseconds. So that's the key problem. Most of the frameworks written in the traditional programming languages address this problem by making use of thread pools. So every time a connection is come to the web server, you take out a pool, a free thread from the pool, and assign the task to that particular thread. How much ever time the thread waits doesn't influence the rest of the workload. Now that's the existing approach. It has a scalability problem, it has a resource consumption problem, because every thread takes as much memory for its thread stack and other resources which it is holding on is actually getting wasted. So the creator of Node.js thought in a different direction. If you don't create more threads in the form of thread pool threads, instead, when a single thread runs your workload, and anytime the thread encounters an IO operation which is involving any of these three endpoints, do some magic or do some peculiar special activity such that the IO operation is delegated to another part of your virtual machine or the operating system or any other software in the stack, and then you continue with the rest of the operation. What is pending in your code, such as taking another piece of request from the client, and as and when the first IO is completed, pause the current operation, go back to the first one, and do what it takes to complete that particular transaction. So that's the whole idea behind asynchronous programming. To achieve that, Node.js have certain modules internally, and Node.js latches on to the JavaScript programming model, which has specific semantics to cater to this particular aspect. The most key question that probably Java programmers ask is, okay, let's take the example of a database operation. I put a select query into the DB, and the DB takes milliseconds. I continue with the rest of the operation, and then at some point in time, the database return the result. Now, how do I switch the context? How do I go back to the original point from where the DB query was issued? I have some additional piece of code that needs to be attached to that, which I wasn't able to run previously because the IO itself was not complete. Now, at this point, I'm at a totally different context. How do I switch the context, right? Do you see the problem? Yes? Yeah. So that's the problem which is addressed by one of the language construct called closure. In Java and C++, that's called Lambda. Closure is a powerful language semantics which basically creates a function in a block of an outer function and remembers the whole context in which the function was created. Now, if you issue a DB query within the context of an outer function, and the outer function encapsulates the whole DB operation, including the pre-query and the post-query activities, and the closure function is actually going to be executed after the DB activity is completed. The closure is able to remember the whole context in which the DB query was executed and able to complete the whole activity. So that's the main reason why Node.js have picked up JavaScript for its asynchronous event-driven architecture. Moving on, this is an illustration of what we just described in the first slide. I have series of asynchronous calls. The first one is a DNS lookup. As you can see, the DNS lookup involves an I/O. It contacts a DNS server and it resolves a name from an IP or an IP from a name. So instead of actually performing an I/O activity, it delegates the request to a DNS abstraction or a DNS API. The API detects that it's an asynchronous call and it composes a request to be passed on to the operating system saying that please resolve this IP address and give me a call back or give me a result at this point or at this point in the control flow. And with that request passed into the dark purple circle in the middle, the control flow goes back to the next line. And in this case, it's a read file operation which follow the suit exactly. Read file is again a IO bound activity. It contacts a file abstraction and requests the driver or the operating system to perform the file read. And instead of waiting for the IO to complete, it goes to the next one, which is a network query. Again, the same thing. The fourth one is a set timeout function. Though there is no IO involved as such here, it's a scheduled activity. And because of that, it follows the same suit, though underneath it doesn't contact the kernel as such. It schedules a time period interval and it fires a control flow once the scheduled time is expired. So it contacts a timer abstraction and the control is passed back to the last line, which is a console.log, where you don't have anything to perform asynchronously. You directly execute that particular code. Now, if you look at the right hand side, you see the last line, which is console.log, gets its result first and then followed by the FSCB and followed by DNSCB, etc. Now, what that essentially means that though the DNSCB was requested first in the program, that's the one which came first. The actual result of DNSCB came at a much later point in time. And other code pieces which were executed at a later point in time, such as file system operation, because file system operation was faster than the network operation, its result came first. Now, the whole idea here is that when the IO activities are pushed onto a abstraction or pushed onto a particular queue or a stack, you are delegating those activities to the rest of the system or the operating system module, which is capable of doing that independent of your control flow, and you are able to freely execute other piece of code in your application. What is the end result? End result is that no blocking in your application. Somebody else is doing your blocking task for you, and the tasks are executed exactly in the order in which their occurrence happens or the actual time that is required for them to complete. So this is the key central aspect of asynchronous event-driven programming, and this multiplexing or this concurrency level is the base for Node.js to be highly successful, Node.js to be high performant, and Node.js to be highly scalable. So at some benchmark says that Node.js for the most common workloads such as web workload performs 30 times faster than the traditional sequential programs. It's not 30%, it's 30 times. So no wonder, because when you run the web workload where too many IO requests happen, for a client it is just two requests, two IOs, one is a request, one is a response. But from the server perspective, every client, if there are 1,000 concurrent clients that are requesting, you have 2,000 IOs. So it's completely IO rich. And in such a software, if you employ such a mechanism, you save a lot of time with a single thread. That's the key thing. You have one single thread which is running all around the place, while you are able to manage every transaction, every piece of code, every piece of IO callback exactly at the time when the IO is completed. The dark purple circle in the middle is called libuv or UV loop, which is central to the event-driven architecture, and the closure, all the callbacks which I mentioned in the code, are central to the asynchronous programming. So I guess you get some basic understanding about Node.js. I'm happy to answer any questions at this point, because this is very central to the understanding of the language or understanding of the framework and platform itself. If not, let's move on to the main topic, tracing. So as I said in the beginning, you could trace your application from many different angles without really writing any instrumentation to the code. So the first one I want to mention here is trace the script or trace the function. Method tracing is as simple as printing the input and printing the output. So in this particular case, you have a number 10 and then the function name, which is local, and then set of input to the function. One is this pointer, and then two numbers 10 and 20. So basically locale function was invoked on a receiver object with two values 10 and 20, and then the next line shows the output of the function, which is a string object, and the value being ENUS UTF-8. The number 10 in the left hand side margin indicates the depth of the call chain, which means there were functions with depth 9, depth 8, depth 7, etc. The function with margin with index 9 is the function which called this method. So if you take the trace file and look backward for the previous numbers 9, 8, 7, 6, etc., you get the whole call chain or the call stack of the application. So this basically means if you want to inspect some of the functional flow of your application, including the input and output, and including which function called which function at what point, etc., this is as simple as applying -- trace option. Next one is tracing garbage collector. So at some point in time, your application is misbehaving and you want to make sure it's allocating memory as per your expectation, and it's deallocating memory as per your expectation. This is more important in transactional workload, where after every transaction you are expecting some amount of memory to be garbage collected. Otherwise there is a memory leak, and after some level of transactions, your application is going to be crashed due to out of memory. So in this example, the output of the -- trace GC shows the scavenge collection example. The millisecond, or even before that, the hexadecimal number indicates a unique execution context in the virtual machine instance, and the millisecond shows the cumulative time since the Node.js application was born, and then the type of the GC, which is scavenge. Scavenge GC runs in the nursery, the new space, and the numbers indicate how much memory was before the collection, and after the arrow shows how much memory was occupied after the collection and how much memory is free after the collection and things like that. So in this trace output, it shows 3 scavenge collections at 34, 43 and 68 milliseconds respectively since the start of the application. Now I want to see how the full GC works. Unfortunately, the small sample application which I took was not able to produce a full GC because it wasn't really creating so many objects. So what I did is I compressed my JavaScript heap by applying the second option, which is max all space size to 5 MB, and then applied the trace GC. Now because the JavaScript heap is so constrained, and as and when the nursery heap is full, it was pushing the objects onto the tenured heap, and the tenured heap was getting full faster because the tenured heap itself is smaller now. And then I see the mark and sweep collector kicking in at 152 millisecond, 157 and 163 milliseconds respectively. The semantics do not change, everything remains same. The number shows what is the memory before and what is the memory after. Next one is tracing the Turbofan. Turbofan is high performing just-in-time compiler that is embedded in the V8 JavaScript engine, which Node.js make use of. So as we know, JavaScript is pretty slow compared to other languages because it's dynamically typed and it has a loose definition of objects. You can, add fields to the object at any point in time. Then you need to maintain a graph or a map underneath to figure out what is the shape of the object, and when you execute code based on the object field and things like that, you need to figure out what is the shape, where the field is sitting, whether there is a change in the field dynamically. So that whole activity in the virtual machine takes a lot of time, and because of that JavaScript is pretty slow, but not in the production, not the JavaScript which we know in the Node.js. What is the difference? There is a just-in-time compiler called Turbofan, which understands the internals of the language, which understands the semantics, and it extrapolates the intention of the programmer. It makes certain assumptions, and it finally translates the script into native compiled code, and that compiled code is able to provide you the necessary throughput at real scale. So -- trace turbo shows which are the methods being picked up for compilation, and it shows 2 lines, begin compiling and finish compiling. So how do you use it in your application? For example, when you're running a workload for a long amount of time and suddenly you see some problems happening in your application. For example, a function is returning an incorrect result, or a transaction is failing with bad result or bad outcome. Now, you know that this function, which is failing now, has been executed for the last 1 week or so, but suddenly what happened to the function? Nobody changed the code. So the most obvious suspect is the JIT compilation, because JIT compilation kicks in at a later point in time when it deems that the method is hot. So then, because the JavaScript code is now executed in the native way, it is so possible that there is some bug in the compiler because of which the translation did not happen in the true manner, and thereby you get a wrong result. So once you apply -- trace turbo and able to locate one method being compiled soon before you see the bad behavior in your application, the most obvious suspect is that method compilation. Then the next action is to skip that method from being compiled and run your test, run your application, and see if you get the correct result. And then definitely you isolate the problem to the JIT compilation of that method. Next stage would be collect the compilation trace for the method, which is basically a step-by-step transformation of the code from JavaScript up to the machine code, and see where the transformation went wrong. Of course, that requires a lot of skills, but that's a good level of isolation that you perform, and then any just-in-time compiler expert can help you to find out what is the problem. --trace OPT provides additional level of information on the optimizing compiler. So here it shows the native pointer or the native address of the method being compiled, the name of the method, and the reason why this method is picked up for optimizing compiler. So in the first case, it says the method is hot and stable. That means it was profiling your application. It was looking at what type of script is being executed, what are the methods that is being called, etc., and found that this particular parse method found to be really hot, executed every time. So it is worthwhile to compile that, to optimize compile that. Next, now the obvious question is, I wrote some JavaScript code and now it is executing in the native format. The assembly instruction or the native object code is being executed because of the just-in-time compiler. What is the guarantee that the transformation has taken place in the right manner? Or I am an expert in the assembly instruction also. I want to see what is the type of code that is being generated for my script. So here is a trace option --print code, which will also show you the generated binary against each of the script. So in this output, the top one shows the script which you wrote, the bottom one shows the optimized code that is generated on the fly. Next one is tracing all the exceptions. So in some exception scenarios, we have seen that most of the cases JavaScript exceptions show the call stack with the line numbers and the function names or the script names properly sequenced. But in some exceptional scenarios, you might need additional information such as the frame count, frame number, or the PC count and things like that, or additional error information. So apply this option --print all exceptions to get those additional details. Now, now that we covered most of the aspect of your program, let's look at how do we debug performance. Performance debugging is one of the toughest thing because you don't know where the bottleneck is coming in the whole of the software stack. Your application, the middleware, or the language runtime, operating system, hardware, and things like that. So the most common use case for performance regression or performance problem comes in two ways. One is your application has changed between two versions. You have a baseline and you have a new version, and baseline is good, new version is bad. Second use case is your application did not change at all, but the underlying stack, one of the elements, got changed between the two. For example, in this case, Node.js version, you switched from version 8 to version 10 and you start seeing performance problems. So Node.js 8 is a baseline, Node.js 10 is a bad one. In either case, you are basically making comparisons. So how do you make comparison? --prof is the option. Run the test with the --prof in the good case and the bad case. It produces a file called isolate and some number and v8.log. It's nothing but the ticks that are collected from your application. So how does the profiler works is it runs an additional profiler thread. It checks what activity your application is performing by looking at the program counter. Program counter is nothing but the machine register which stores the current execution code. So it keeps polling that particular register, and from the register it figure out which part of the application is currently being run and make a intelligence out of it. So the v8.log stores a encoded format of the tick sample information. By applying --prof process, you get a readable format of the trace output. So in this case, you see lazy compile of foo has taken 13,384 ticks. That means every time the sampler sampled, you found this method on the stack. That means this is always being executed. It could be that it has a infinite while loop, or it's a service method of the servlet or your HTTP service loop, and then you go beneath that, you see once wrapper method, which is again found in 13,384 ticks, and it shows 100%. So what that means is every time foo method was executed, once wrapper was also called. So all the CPU that is consumed by foo basically is attributed to once wrapper. So the whole idea is module.run main was being executed all the time, and this is the call stack of the current application, and the only inference you can make is module.run main, which is in the bottom of the stack, is having a tight loop, and every time you're running, you're seeing it over there. Now that was not the point which I want to make. Get the profiler output for your baseline, get your profiler output for your problem state, and compare the heavy profile and see what is the inflection point where the numbers are deviating, where you see more ticks in the bad case, where you find more ticks in the good case, and then that gives you the first level of isolation. That's about profiling. Now, so far we looked at the application from all different angles without ever changing any source code. Now, what if you are not happy, or none of these tracing options are able to provide you the information which you wanted? For example, the -- trace option gave you the function input and the function output. What if I want to inspect a value somewhere in the middle of the function? None of these explained features are going to help. So you are talking about following the control flow of your application at every arbitrary points, right? So the only option which I can think about is live debugging and LL node, which is a LLDB extension. LLDB plugin provides you with that option of live debugging. In live debugging, you just launch your application through LLDB and put breakpoints at whatever control flow points of your interest. The beauty with LL node, unlike any native debuggers, is that it shows you the JavaScript methods as well as the native methods as if they all were of same family or same group. On the other hand, if you are launching your application through a native debugger, you just see the C++ methods. You don't see the JavaScript, or you don't see any methods of managed runtime. If you are debugging a Java, you don't see the Java methods. If you are debugging Python, you don't see the Python because they are not native methods. They are, simulation. They're abstraction by the virtual machine. So LL node de-abstracts those elements and figure out for every PC what is actual JavaScript method being executed and reconstruct the frame so that for the end user, you get a feeling about your debugging a single monolith application. Having said that, we have a new diagnostic report tool launched in Node version 11 onwards. It's very handy. How does it work is you apply -- experimental report on your application and collect the report at whatever points of your interest by triggering a signal to the running application or calling an API from within your application at any point of your control flow, at any point of your interest. So it gives you a comprehensive holistic view of the Node.js runtime. It shows you the header, the trigger, the version, operating system, glibc, and the architecture, etc. It shows you the JavaScript stack, it shows you the native stack, and it shows you different elements of the JavaScript heap. JavaScript heap is actually categorized into 5 different spaces: the tenured heap, also known as old space, the new space, also known as the nursery. Then you have the code space, which stores the just-in-time compile code, and large object space and things like that. Against each of the space, it shows you what is the total memory, what is the allocation, and what is this free space. Then it also shows you the resource consumption details against the kernel space and the user space, shows you what is the file system activity, etc. And it shows you the shared libraries that are linked against your application. Let me see if I can show you the code. Yeah. So node. So this is the diagnostic report. It has a couple of APIs to write the report into a file, to get the report in the form of a object back into your application. You can set the location where the report needs to be generated. You can set the file name of the report, and you can define which signal you want to issue to the application, so that application triggers a node report, diagnostic report. And you can define at what control flow points you want to trigger the diagnostic report, whether on an error, whether on a signal or an exception, etc. So in this case, I'm just creating a report. So it produced a report. The other key feature of the report is that it's in JSON format, which means you can read it if you are interested, and you can pass it on to another software, which is like a monitor or a any other software which you want to make abstraction, make insight about what your application is doing, etc. So it's a semi-man machine readable format. So it shows you the header, the command line, Node.js version, architecture, and each of the internal components and their versions, operating system name, JavaScript stack, which we looked at, native stack, the PC, which is part of the native stack, JavaScript heap, and the resource usage, and the libuv. Yeah, this is one of the things which none of my tracing options covered, and none of the existing tools can capture. For example, what if you are running a highly concurrent workload and you want to know what is the state of your libuv event loop? You are facing some throttling, you're facing some latency problem, concurrency, or overall throughput issue. You want to know that your libuv loop is in good health and condition. It's not really congested, or the rate at which the requests are coming is actually being handled in a proper manner by the libuv. What are the active handles sitting in the libuv loop and things like that. So the diagnostic report provides you an insight about the libuv, how many handles, what are the type of the handle, what is the native address, is it active or not, etc. And then the whole environment variables and the ulimit on the shell, and finally the shared objects which are linked in this process. So very handy. You don't need to instrument your code at all, and you don't need to apply any command line options in the beginning. Of course, dash dash experiment report, but the amount of information you get through getting a report is really tremendous. And without knowing what type of problem you are diagnosing, just by looking at the report, you might be able to figure out what is happening. Not only used for problem determination, but also to check what is the health, how is the health looking like for your application at regular intervals, and you can build abstractions on top of that. For example, monitoring and other systems. So that's the whole thing I want to discuss. Everything that we covered today is available in each of these links. First one is Node.js community website. Next one is the W3 schools, which is very good for learning JavaScript, and the V8 help is provided. Every tracing option which I showed today and any other additional options, exhaustive list of options, are obtained through applying that flag, and the help on the usage of diagnostic report. And finally, if you have specific problems on usage of Node.js or any programming query or clarification that is required or any support that's required, Node.js/help repo is the specific project area where you can ask questions. The community, as I said, is really active and very happy to provide help. Yeah. Oh, okay, sorry. So here is the Node.js community repo. This is W3 schools, and this is the V8 help. And for additional diagnostic options, tracing options, you apply this flag on your command line. And this is the help repo for the diagnostic report. This is basically part of the API documentation. If you go to the green website, you click on the API docs, one of the options you get is the diagnostic report, and this is the repo name for the Node.js help. I just want to reiterate the fact that Node.js is a very active community, and you have space for JavaScript programmers, you have space for C++ programmers and C programmers. libuv is written in C, Node.js virtual machine is written in C++, V8 is written in C++, and the core API is fully written in JavaScript. So based on your skill, based on your choice, based on your interest, you can choose any items. And if you look at the project repo, we have around 700 issues in the backlog. We have around 200 pull requests that is open. So despite the fact that we have 2,000 plus contributors and 100 plus collaborators, still the project requires a lot of people. So welcome, and really happy to have you getting engaged over there. Just want to complete my presentation with this particular aspect, Call for Code. It's an initiative that is run by IBM plus the UNESCO and American Red Cross Society. Basically, the whole idea is to run hackathon kind of event year on year. Look at how the cutting edge latest technologies such as cloud, AI, data analytics, and other technologies to be able to address the most perennial problems of the society, such as natural calamity and things like that. There's a huge prize money, $200,000, I guess, and it's a good opportunity to collaborate with software engineers across the world. It was a huge success last year. I think this is the time for registration. So I just want to request your consideration and taking part in this particular activity. Thank you so much.